So in this PowerPoint, we will be talking about dipole moment, which has to do with electronegativity and charge distribution. Dipole moment indicates whether a molecule is polar or not. Dipole moment, which is mu, Greek letter mu, is when a molecule can move in the presence of an electric current. The higher the polarity of the molecule, the higher the dipole moment. Dipole moment is actually a number which is measured quantity, so it's not just a random thing, it's actually a measured number that's given. So the higher that number is, the higher the dipole moment is. Ionic compounds are going to be inherently polar because of the presence of ions. The ions are cations and anions, and so because of those two, it's polar automatically, and so it has a really high dipole moment. Diatomic molecules that have the same atoms, like hydrogen, chlorine, iodine, these are also called homotopic molecules. These are going to be nonpolar because there is no difference in electronegativity. In this chapter, or for dipole moment, you really have to know electronegativity well, which we've done in chapter 1 already. So you should know what the trends are for electronegativity. And you will also have to kind of remember some of the differences in the bond. So for example, when you have a polar covalent bond, that polar covalent bond is because the electronegativity difference between the two atoms is more than 0.5. If it's less than 0.5, then it is a nonpolar bond. So for example, CH bond, CI bond, those are nonpolar bonds. Okay, so those are some things that you have to remember. Again, I wouldn't say, do all the calculations all the time, but know the trend. So any molecule that has a polar covalent bond can have a dipole moment, and that depends on the shape. And so the shape is important in the sense it means if you have a symmetric shape or an asymmetric shape, all right, that's when it can have a dipole moment. And of course, it's also dependent on the electronegativity or the polar covalent bond, which again we did in chapter 1. So make sure you review that. So how do you determine the dipole moment of any molecule? Well, these are the steps that you take, and if you follow them straightforward, then you should not have any issues at all. So first of all, write the Lewis structure. Write the correct Lewis structure of any molecule, which means write all the lone pair of electrons, and especially on the central atom, because that will help you to determine the shape of the molecule, which is the second step, and that is determine the shape of the molecule. Shape of the molecules, of course, is bent, trigonal planar, trigonal pyramidal, tetrahedral. Those are the 4 shapes, and linear. Those are the 4 or 5 shapes that we deal with in organic chemistry. The third thing is to identify the polar covalent bonds in the molecule. That is where you need the periodic table, and you need to know the difference in the electronegativity. You don't have to know the numbers. A general trend is good enough. And in some cases, if you do a few examples, which means if you do a few subtractions, then you can kind of keep in mind about which bonds are polar and which are not so polar covalent. So for example, the Ci bond is not that polar, however, the CCl bond is quite polar, okay, in its nature, which means that the difference in the electronegativity is a lot more for CCl bond than for the Ci bond. So if you do a few of these calculations in advance, you will have something in mind at least, okay, of what's a polar bond and what's not. Then, of course, you see if there is an asymmetric pull in the molecule, which means is there asymmetry in the molecule or symmetry in the molecule. So this is the last step that you do for dipole moment, and this is one of the most important steps also, which you can do only if you have the shape right. And again, you can get the shape right only if you have the Lewis structure correct. So all of these steps are important steps. The 3 molecules here, water, methanol, ammonia, these all have very high dipole moment, so mu. And then this is D, capital D is dpi, and that is the unit for dipole moment. So for water, there is a dipole moment. Dipole moment is indicated by this arrow with a little cross here on it. And the arrow points towards the negative charge, where oxygen is more electronegative than hydrogen. So oxygen has the delta negative and hydrogen has the delta positive. So the arrow is pointing more towards the negative side. Here, this is methanol. And in case of methanol, oxygen is more electronegative than carbon. And because of the shape of the molecule, which is bent, there is an asymmetric pull towards oxygen, okay, and that's where the arrow is pointing then. In case of ammonia, nitrogen is very electronegative, and so there's an asymmetric pull towards nitrogen, and that's where the arrow is pointing then. Please remember, this arrow that is pointing has a crosshair on it, and this is the only arrow that we use for dipole moment. Here are some examples of dipole moment of some molecules. So you can see here sodium chloride 9. That's really very high, okay, and that's because it's an ionic compound. So as I said, inherently that's going to be of a very high dipole moment, okay. And then CH2O, if you don't know the Lewis structure of this, you should draw it out. Of course, the highly electronegative elements like oxygen, nitrogen, and fluorine will all show very high dipole moments unless there is symmetry in the molecule. But otherwise, most of them will have really high dipole moments. So by the time we come to these molecules here, they have very low dipole moment or zero dipole moment. So carbon dioxide, methane, and then ethane, benzene, no dipole moment. So these are the structures of the molecules that have no dipole moment, and you can see that they are symmetrical in nature, okay, which means carbon dioxide, which is carbon in the middle and oxygen on either side, is a linear structure. And even though carbon and oxygen is a polar covalent bond, but because the pull is equal on both sides of carbon and because of its linear shape, the dipole moment is zero. So it's almost like a tug of war. That's how I see dipole moment. So if the atoms are pulling equally on either side, then they nullify each other. Same thing happens with methane. The other thing about methane is that the carbon-hydrogen bond is not that polar to begin with. However, in this case, it's a symmetrical molecule too. Same here goes with ethane and then benzene. All of these are symmetrical molecules, and in some cases, like carbon dioxide, the dipole moment will kind of nullify each other because, or the polar covalent will nullify each other because of the symmetry in the molecule. So there is no dipole moment in these cases. So what is the purpose of the dipole moment? Why do we need to know it? In any case, in fact, in all cases, not just organic, it's really helpful in determining the physical property of the molecule. So it's really important you know the dipole moment. It's not important to know the exact number. It is important to know which molecule will have a dipole moment and which one will not, which one will have low or high. So as a comparison, one should know, okay, what the dipole moment is, not the actual number of it. So in any case, what are the physical properties that we will be talking about in organic for dipole moment? One of them is solubility. And so polar molecules will dissolve in polar substances. Okay, so like dissolves like, that's how the rule goes. So that's why you need to know the dipole moment here. Boiling points and melting points. The higher the dipole moment, the higher the boiling point and melting point of substances. So for example, sodium chloride is really high melting point because it is polar, has a high dielectric constant or dipole moment. Whereas naphthalene or benzene, they have very low boiling points because they have no dipole moment. And carbon dioxide, if you know, of course, it's a gas, okay, because it has no dipole moment. Vaporization, and so this is dependent on boiling point, and I kind of put it separately because almost all organic compounds are volatile. Volatile meaning that they give off vapor all the time, and the reason they give off vapor all the time is because they have low dipole moment, okay, in them, and that affects their intermolecular forces, which we're going to talk about. So if the intermolecular force is low, and that is because the dipole moment is low, then compounds will start vaporizing, okay, because they have low boiling points. There is no attraction between molecules. So vaporization is a really important thing for us because a lot of organic compounds are flammable, and if they're vaporizing, it means that you have a lot of flammable